Hey everybody, my name is Navjeet Singh. I'm an undergraduate student of the City College of New York, and I'm going to be conducting a performance-based study on two actuators. The first being the series elastic actuator, and the second being the quasi-direct drive. Here's a quick overview. I'm going to be first discussing actuators, then I'll be diving deeper into bandwidth and backdrivability, and then we're going to be concluding this topic off with an analysis on these two performance metrics. So what is the function of an actuator? Actuators operate by a control signal sent from the controller, and it provides mechanical motion. As you can see on the table below, we have the maximum torques for the knee, hip, and ankle joints at 40, 65, and 125 Newton meters, respectively. Ideal actuators would incorporate low speed and high torque. And some common challenges that we face when selecting an actuator is the mass of it, as well as the resistance. The SEA series elastic actuators are one of the most used actuators in the robotic industry, especially in exosuit manufacturing. And it incorporates an elastic element in series with mechanical energy. Bandwidth, simply put, is how fast a system responds to a changing input command. And it is defined to be the frequency range in which the magnitude of the closed loop frequency response is greater than -3 decibels. You can visually see that on the figure on the bottom right. And also the goal of actuators are to reproduce the input signal as precisely as possible. And there's sometimes a trade-off that we have to do, because with larger bandwidths, there's going to be higher frequency noise, and that will, of course, hinder the system's performance. Backdrivability is a measure of resistive force exerted from a system when another force is acting on it. On the video on the right bottom, you can see a user applying very little force on the system. This pretty much indicates that it's going to have high backdrivability. Now, when we open the system, you see that the user has to apply a much greater force just to move the system. This indicates that it has low backdrivability. So we could develop a relationship saying that backdrivability is inversely proportional to resistance force. Here is a table comparing the QDD as well to the SEA. We could see that the SEA includes a spring encoder, whereas the QDD has a low inertia leg, low gear ratio transmission, and high torque density motor. We can also see that the backdrivability and the bandwidth are high in the QDD, as well as having a low mass. Here is a hip exoskeleton model in the time domain. We can see all the governing equations written on the bottom, and on the left-hand side, we can see what each variable represents. Here's a control block diagram showing everything in the frequency domain. And here's how we derive the transfer function for bandwidth, which is essentially the output torque over the reference input. And deriving the backdrivability transfer function is pretty much the output torque over the human joint angle. Here's a control block diagram created on Simulink. We can see here, this is where we can adjust our chirp function, and here's where we can adjust our voltage. These are the given parameters of a typical SEA and a QDD actuators. We can see that the gear ratio is far greater in the SEA over the QDD, as discussed earlier. Here are the results for the bandwidth. We can see that the SEA bode plot diagram shows us that the cutoff frequency is at 11.29 hertz, whereas for the QDD bode plot diagram, we notice that the cutoff frequency is at 88.72 hertz. This pretty much shows us that the bandwidth is far greater in the QDD. For the backdrivability results, we notice that the resistive torque in the QDD is 1.272 Newton meters, and we can see in the SEA it's 3.335. The QDD has a higher backdrivability relative to the SEA because it has a lower resistive torque. And these are the project references. Thank you for watching.